Okay, so recall the first question we started to explore when we introduced linear algebra was, okay, I have a vector y, and I have this other vector x. Of all of the vectors that are in the span of x, and remember the span of x is the set of all vectors in the same direction of x, so these are all vectors in the span of x, so are these. Of all of those vectors, which of them is the closest to y? Now note that vectors in the span of x are written in the form wx, where w is just some number that I'm multiplying x by to either make it longer or shorter to bring it as close to y as I can. Now with every wx, there's associated an error which shows me how far wx was from y. So this is an error vector. And the idea is that error is bad, so I want to minimize the length of my error vector. So I want to make the length of this red thing as short as possible. And we concluded the last class that the way to do this is by choosing a w that makes the error vector orthogonal or perpendicular to x. And so the ideal setup requires us to choose a w that makes the error vector in x perpendicular. Okay? And when I choose that specific w, it is the optimal or best w, so I'm going to call it w star. And as we can see here, the associated error vector with it is perpendicular or orthogonal. Okay? Now, we found, using properties of linear algebra, what this optimal w star was supposed to be. It was this quantity. Now this quotient here, x dot y over x dot x, what is it? Is it a data frame, a binary search tree? What is it? It's a single number. Okay, that's important. It looks complicated, but this is just a scalar. How did we find this scalar? Well, we said, hey, the w star I want to use is the one that makes the error vector orthogonal to x. And so written out mathematically, the error vector with this best w would look like this, y minus w star x. If I want that error to be orthogonal to x, well then the dot product of the error with x must be 0. And what we did is we solved for w star here. Okay? Now here's a question just to make sure we understand the role of w star. If you had to approximate the value of w star here, what would you estimate it to be? Yeah. Yeah, it's around a half. Why? How'd you get that? Yeah, it seems like w star x seems to be like roughly half the length of x. Okay, and so w star being a half is saying, hey, if you want to scale x so that it's really close to y, well then do x times a half. And when you do that, the resulting vector you get is as close to y as you're going to get. Okay? So in this example, w star is around a half because the length of w star, x, is around a half the length of x. Sound okay? All right. So that was the first case, and it's worth mentioning, again, that w times x is just the way we write some arbitrary vector in the span of X. Okay, so all vectors in the span of X are written in the form W times X, where W is just some number. W star is the best amount or best number to multiply X by if what we care about is picking a vector in the span of X that's as close to Y as possible. Okay, that was the one vector case, but then things got a little more complicated and we said, hey, what if we now have two spanning vectors, x1 and x2? What's the closest vector in the span of x1 and x2 to my vector y? Okay, now here's a screenshot of Jack's animation from last class. Remember, if we have two spanning vectors, x1 and x2, the span of x1 and x2 is the set of all other vectors I can make using linear combinations of x1 and x2. And from the animation we had, we saw that the span of two vectors, assuming they don't point in the same direction, is a plane, right? And so that's what this like grid here represents. This plane is the span of x1 and x2. Okay, so the question is, of all the vectors in this plane, each of which I can make by doing a linear combination of x1 and x2, of all of those, which of them is closest to y? That is, which one has the smallest error vector when I see how far it is from y? And the answer is the one whose error vector is perpendicular to this plane. That is perpendicular to both x1 and x2. Okay? And so the setup might look something like this. That doesn't look totally perpendicular to me. Okay? Where this is the error vector that I'm targeting. And it's orthogonal to both x1 and x2. Which means it's orthogonal to the entire plane spanned by x1 and x2. This vector then, this shadow of y, when you cast it onto this plane of combinations of x1 and x2, that is the projection. And it's of the form w1 star x1 plus a w2 star x2. Okay, that's saying, hey, any vector on this plane is of the form w1 x1 plus w2 x2. That's what I have here. All the vectors in this plane look like this. My question is, what is the best w1 and the best w2? Well, it's the w1 and w2 that make it so that the error vector is orthogonal to this plane. Okay? Why do we want the error vector to be orthogonal to the span of x1 and x2? Well, it's because that's how you make it as short as possible. And again, in Jack's animation, we saw that if we move the projection somewhere else, well, then the error vector gets longer than it is right now when there's a 90-degree angle. Okay? Questions with the setup? We are trying to find the vector in the span of x1 and x2 that's closest to y. Okay? How did we do it? Well, we turned to the power of matrices. We said, hey, it's kind of annoying to have to keep saying w1 x1 plus w2 x2, especially because soon maybe we'll have 3 spanning vectors or 4 spanning vectors or 70 spanning vectors. And it would be annoying to do w1 x1 plus w2 x2 plus w3 x3 70 times. So instead we said, hey, we can take those two vectors that we're dealing with, x1 and x2, and stack them next to each other in a matrix. Okay? In a matrix that I'm going to call just capital X. Now in this case, since my individual vectors had 3 components, and there were 2 of those vectors, X has dimensions 3 by 2, 3 rows and 2 columns. Okay? Now, any linear combination of x1 and x2, I can express as the matrix X times this new vector w, where the vector w consists of the number I multiply x1 by and the number I multiply x2 by. So that is all to say, any linear combination of x1 and x2 can just be written as capital X times vector w. Why is that? Well, it's because when I work out this multiplication, which is this matrix times this vector, what it's going to end up doing, as we saw last class, is multiply w1 by this column, and to that add w2 times that column, which is the same as w1 times x1 plus w2 times x2. Okay, so it's an easier way of writing linear combinations of vector x1 and vector x2. Okay? And so my goal is still the same. Like all this is just another way of reorganizing the information I have. The goal is to find the w that makes the error vector y minus xw. Again, the xw here is just the new w1x1 plus w2x2, orthogonal to every column of x. Okay? That's still my goal. Find the w's that make the error vector orthogonal to every column of x. And just to really drive home this point, xw is just the new w1x1 plus w2x2. Okay? Now how did we do that? How did we find the w that makes the error vector orthogonal to every column of x? First, taking a step back, why do we care? Well, it's because finding the w's that make the error vector orthogonal to every column of x will find us the error vector that is as short as possible. And remember, the idea is that error is bad. We want it to be small, so we want the length of the error vector to be as small as possible. Okay? Our conclusion towards the end of the last lecture is that the w star that makes this happen, that is, that makes the error vector be orthogonal to every column of x, satisfies x transpose error vector equals 0. Now at first this may seem strange because x transpose times the error vector equals 0 doesn't involve a w or a w star. Or does it? Where is the w in this equation? Any ideas? Yeah, the error vector involves a w, right? This is really just x transpose times y minus xw star equals 0. I'm writing a star here because this is a condition that the best w vector will satisfy. Other w vectors will not satisfy this. Okay? And so this is the goal. It's to find the w vector that satisfies this. Why? Why do we care about this particular property? Well, remember, the X matrix, I constructed it by taking my two vectors, x1 and x2, whose span we were trying to project onto, and I put those two vectors next to each other in one matrix, which in this case had 3 rows and 2 columns. What I want is for each of these columns, x1 and x2, to be perpendicular or orthogonal to the error vector. Okay? And remember, an equivalent condition for two vectors being orthogonal is that their dot product is 0. So equivalently, what I'm looking for is the dot product of this column with the error vector to be 0, and the dot product of this column with the error vector to be 0. That's what I'm searching for. And recall, when we introduced matrix vector multiplication, we saw that something like AV is the dot product of V with every blank of A. What goes in the blank? When I multiply out A times V, what I compute is the dot product of V with every what of A? Yeah. Yeah, it's the row of A. Okay? And the result is a new vector too, which means X transpose E, which is also a matrix vector multiplication, the result of this is also a vector. Okay? But I don't want the dot product of X's rows with E to be 0. I want the dot product of X's columns with E to be 0. So how do I change rows to columns? I transpose. And so by taking this multiplication of X transpose with E, what it ends up computing is this new vector with 2 rows and 1 column, which contains the dot products of every column of X with E. The reason it's the columns of X and not the rows of X is because I have this transpose here. And that's what I want. I want the dot product of every column in X with the error vector to be 0. So computing the product X transpose error vector and setting that to 0 satisfies this for me. Note that this first element here is just the dot product of x1 with the error vector. Remember, A transpose B is the same as A dot B. Okay, and so this is a vector with 2 dot products in it. The dot product of the first column of X with E and the dot product of the second column of X with E. And the idea is by setting this to 0, it's saying I want both of these components to 0. So to be precise, this should not be the scalar 0, but it should be the 0 vector. Is that something you talked about in Math 18, the 0 vector? Yeah, this is the 0 vector. Okay, so big picture, a lot of stuff there. Big picture is that I want to find the error vector that is orthogonal to every column of X. And the error vector that satisfies this satisfies X transpose the error vector equals 0. Okay? And that gives me a recipe that I can use to find the W star that makes this all happen. And remember, the W star, it contains the secret information that I use to figure out how much to multiply x1 by and how much to multiply x2 by to get the best projection of y into the span of x1 and x2. And so the way I find my W star is by starting to substitute y minus xw star in for the error vector. And again, there's a star here already because I'm saying the best W vector will satisfy this sequence of equations. Other W vectors may not. But we're talking about the best W vector here, so there's a star. What I can then do is distribute this multiplication. So I have x transpose y minus x transpose xw. And then I can rearrange this equation to have this statement, which is important. It's saying, hey, the W star that will make your error vector orthogonal to every column of X will satisfy this equation. But this equation I called the normal equations, plural. Why is it plural? Why is it called the normal equations? Yeah. Yeah, it's because x transpose x is a matrix, and W is a vector, which means that this is actually a system of equations. There's actually 2 equations, because there's 2 components in the W vector, W1 and W2. So this is a system of equations. Okay? Now, these are the normal equations. What we were saying is that the best W you will find to make your projection of y onto the span of x as close to y as possible will satisfy this. Now, in some cases, we can isolate a formula just for W star. But to do that, we need to be able to multiply both sides of this equation by the inverse of x transpose x. How that would look is by taking x transpose x inverse and multiplying it on the left by both sides. Because if we add x transpose x inverse here, that will allow us to cancel things out. Now, multiplying by the inverse is kind of like dividing, right? So just as an aside, if we have something like 2x equals 5, to isolate for x, I mean, what we would do is divide by 2, but what that's really doing is multiplying by the inverse of 2. Okay, no one really thinks of it that way, but that's what you're doing. Well, I shouldn't say nobody. Maybe you do think of it that way. But that's what we're doing over here. Okay, we're multiplying both sides by the inverse of x transpose x. But that requires x transpose x to be invertible, which it may not be. Okay? Question, are we familiar with the term full rank from Math 18? Are we familiar with the idea of the rank of a matrix in Math 18? Interesting, because most people here are saying no, but most people in the first section said yes. But you all presumably took the same Math 18 at UCSD. The idea behind a matrix being full rank is that all of its, well, there are many equivalent definitions, but the one that will be useful for us is that all of its columns are linearly independent. Okay? And it requires x transpose x to be full rank, but a property that, it's not the kind of thing that we're going to prove here, but it's true, and it's maybe something that you learned in Math 18, maybe not, is that an equivalent condition to x transpose x being full rank is that x is full rank. Okay? And, taking a step back, why do we need this to happen? Like, why do we need all of the columns of x to be linearly independent? Well, if it doesn't, well, then you can't multiply on the left by x transpose x inverse. And so there are actually infinitely many solutions to the normal equations, which means there's an infinite number of W1s and W2s that will make your projection as close as possible to y. Okay, this is kind of a strange idea. Like, one of the questions I got in the last lecture was, does this mean there is no closest vector in the span of x to y? And no, it's not. It doesn't mean that. But think of it like this. Strange example, but let's suppose you're trying to get as close to Panda Express in the Price Center as you can. But for some reason, there are a lot of barriers or barricades set up around Price Center. Maybe there's like 7 locations that are all equally close to Panda Express, and they're all as close as you can get to Panda Express. So in that situation, there are like 7 closest possible places you could be. Okay, and they're all as close as possible, they're just all equally close, right? Same kind of setup here. If x transpose x isn't invertible, there are just infinitely many W stars that make your projection as close as possible to y. There's not just a unique one. Sound okay? Yeah.
Does that mean that y is like perpendicular?
No, it doesn't necessarily mean that y is perpendicular to x. Why, this, the x's and their independence or not independence has nothing to do with y directly, right? Good. Okay, so taking a step back, what do we gain from all of this? What was the point? Well, remember, the question we started off trying to answer was, of all of the vectors that exist in the span of x1 and x2, which of them is closest to y? That is, what number do I multiply x1 by, plus what number do I multiply x2 by, to make a vector that's as close to y as possible? What we did with all of this x transpose x business is we answered that specific question. Okay, it said, hey, the numbers you multiply x1 and x2 by come from solving the normal equations. okay, which, if x transpose x is invertible, gives us the vector w star equals x transpose x inverse x transpose y. And so that's a concrete formula you can plug into the computer, and it's the kind of thing we're going to do in a few minutes when we switch to a notebook. But when I did it for this matrix x and this vector y, it gave me 0.7289 and 1.6300, which tells us the right number to multiply x1 by was 0.7289, and the right number to multiply x2 by was 1.6300. So it's saying, of all the different numbers you can multiply x1 and x2 by, and add them to create a vector in that plane that x1 and x2 span, this is the one that's closest to y. Okay, that means what I've highlighted here is this vector. It's the one on the plane that is closest to y. That's concretely what the point of all of this was. Okay, questions with what we've seen so far? Sound okay? All right. Now, taking a step back, it turns out that we implicitly solved an optimization or a minimization problem without explicitly saying that we were going to do that. And the problem that we solved is actually quite similar to minimizing mean squared error and minimizing mean absolute error like we were doing towards the beginning of the quarter. Okay? What I have here is the length of the error vector. And the only thing I really get to change, the only unknown, is the vector w. Because x is assumed to be given to me, and y is assumed to be given to me. The question is, how close can I make my projection of y onto x, the columns of x, to y? Okay, and that how close can I make it is the length of the error vector. The amount that I multiply the columns of x by to create this linear combination come from w. And so that's the only unknown. Like, how much do I multiply the first column by? How much do I multiply the second column by? Okay? What we learned using properties of linear algebra is that the w star to use, that is the w that minimizes the output of this function, is the one that satisfies the normal equations. Okay, which, when x transpose x is invertible, gives us this solution. Okay, so that's the key idea here. We did a optimization problem without having to use calculus directly. Now, it is possible to use calculus to minimize this function. It's a thing. Okay, and in fact, that's how previous versions of DSC 40A used to introduce this topic. I changed it this quarter. Why? Well, it may seem like whatever we've done now is painful, but I assure you it is much less painful than whatever we would have done if we did it the other way. Okay, and even if it may have been a little more painful now, I can promise you that when you take future classes like DSC 80 or DSC 140A, you'll understand it a lot better now that we went through all of it.